It started back in September 2008. Clearly something serious was going wrong with our economy at that point, and it occurred to me at that time that the crisis was being framed in terms that were too narrow, that only accounted for what was going on within the financial industry. But it seemed to me that there was something more to the story than that. So I started talking to people. I began interviewing people on Wall Street, former managing director of J.P. Morgan, various retired hedge fund managers. There's a theme quickly emerges here. I tend to talk to retired people a lot because very often they know where the bodies are buried and they're willing to tell you. But a lot of former Wall Street people and a number of economists who work closely with energy and resource issues spoke also with people in the resource industry, petroleum geologists and others. My book has pages of acknowledgments, so I won't try to name everyone here. But very quickly, a picture started emerging that was very, very different from the one that we are accustomed to hearing through the media and through most of our political representatives. It's a very disturbing message, but it's one that I think is absolutely essential that we have as part of our national conversation. Because if this is true, it has enormous implications not only for our economy, but for our political system and just about everything else. And I think it needs to be part of that conversation. If this is true, then we need to adapt to a fundamentally new economic reality. I'm suggesting that we are at a decisive turning point in our economic history, the end of economic growth as we've known it. Now, economic growth is something that every politician promises, and that every economist, or nearly every economist, I'd say well over 90% of economists believe is the normal and natural state of modern economies. However, nothing grows forever on a finite planet. We assume economic growth, and yet we live on a planet of limited resources. So common sense says that at some point we will reach limits to growth. I'm suggesting that we've done so, and just recently. Well, in order to tell you the story, give you some context, I have to start with energy because, well, first, energy is sort of excuse me, sort of my subject. I've written several books on it, but also the reason I'm interested in energy in the first place is that it's the prerequisite for everything else. All economic activity depends on energy.
And what I hope to do is I hope to be able to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So you say, well, what's the exponential function? This is a mathematical function that you would write down if you're going to describe the size of anything that was growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about, it's ordinary, steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now that longer time is called a doubling time. We need to know how you calculate the doubling time, and it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. So our example of 5% per year, you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Well, you might ask, where did the 70 come from? The answer is it's approximately 100 multiplied by the natural logarithm of 2. If you wanted the time to triple, you'd use the natural logarithm of 3. So it's all very logical. But you don't have to remember where it came from if you'll just remember 70. Now, I wish we could get every person to make this mental calculation every time we see a % growth rate of anything in a news story. For example, if you saw a story that said things have been growing 7% per year for several recent years, you wouldn't bat an eyelash. But when you see a headline that says crime has doubled in a decade, you say, my heavens, what's happening? Well, what is happening? 7% growth per year. Divide the 7 into 70, the doubling time is 10 years. But notice, if you're going to write a headline, you never write crime growing 7% per year, because most people wouldn't know what it really means. Now, do you know what 7% really means? Let's take another example from Colorado. The cost of an all-day lift ticket to ski at Vail has been growing about 7% per year ever since Vail first opened in 1963, and at that time you paid $5 for an all-day lift ticket. Now, what's the doubling time for 7% growth? 10 years. So what was the cost 10 years later in 1973? 10 years later in 1983? 10 years later in 1993? And what do we have to look forward to? Now, this is what 7% means. Most people don't have a clue. Well, let's look at a generic graph of something that's growing steadily. After one doubling time, the growing quantity is up to twice its initial size. Two doubling times, it's up to 4 times its initial size. Then it goes to 8, 16, 32, 64, 128, 256, 512. In just 10 doubling times, it's 1,000 times larger than when it started. And you can see, if you tried to make a graph of that on ordinary graph paper, the graph will go right through the ceiling. Let's look now at what happens when we have this kind of steady growth in a finite environment. Bacteria grow by doubling, and one bacterium divides to become 2, the 2 divide to become 4, the 4 become 8, 16, and so on. Suppose we had bacteria that doubled in number this way every minute. Suppose we put one of these bacteria in an empty bottle at 11 in the morning and then observe that the bottle's full at 12 noon. Now, there's our case of just ordinary, steady growth. It has a doubling time of 1 minute. It's in the finite environment of one bottle. I want to ask you 3 questions. Number 1, at what time was the bottle half full? Well, would you believe 11:59, 1 minute before 12, because they double in number every minute. And the second question, if you were an average bacterium in that bottle, at what time would you first realize that you were running out of space? Now think about this. This kind of steady growth is the centerpiece of the national economy and of the entire global economy. Think about it. Well, let's just look at the last minutes in the bottle. At 12 noon, it's full. 1 minute before, it's half full. 2 minutes before, it's a quarter full, then an eighth, then a 16th. Let me ask you, at 5 minutes before 12, when the bottle's only 3% full and is 97% open space just yearning for development, how many of you would realize there was a problem? Now, in the ongoing controversy over growth in Boulder, someone wrote to the newspaper some years ago and said, look, there isn't any problem with population growth in Boulder because, the writer said, we have 15 times as much open space as we've already used. So let me ask you, what time was it in Boulder when the open space was 15 times the amount of space we'd already used? And the answer is it was 4 minutes before 12 in Boulder Valley. Well, suppose that at 2 minutes before 12, some of the bacteria realize that they're running out of space, so they launch a great search for new bottles. And they search offshore, on the outer continental shelf, in the overthrust belt, and in the Arctic. And they find 3 new bottles. Now, that is a colossal discovery. That discovery is 3 times the amount of resource they ever knew about before. They now have 4 bottles. Before the discovery, there was only 1. Now, surely, this will give them a sustainable society, won't it? Well, you know what the third question is. How long can the growth continue as a result of this magnificent discovery? Well, let's look at the score. At 12 noon, 1 bottle's filled. There are 3 to go. 12:01, 2 bottles are filled. There are 2 to go. And at 12:02, all 4 are filled, and that's the end of the line. Now, you don't need any more arithmetic than this to evaluate the absolutely contradictory statements we've all heard and read from experts who tell us in one breath we can go on increasing our rates of consumption of fossil fuels. In the next breath they say, but don't worry, we'll always be able to make the discoveries of new resources that we need to meet the requirements of that growth.